you had this extra term. So that means that your input was biased. And the question was, so if you have an input in your bias, is your Kalman filter biased? You calculate the expectation. You saw that it was not, the error was not 0, right? And I think most of you answered this correctly. But for those of you who didn't, this was a little misconception. I didn't penalize on this, but it was not really well written. Not perfectly written, let's say. Okay, this is I think the main thing, and then, well, there's little errors here and there, but if you want, we can comment them later after class with TAs, or you can send me, you can also review results if you don't agree, right? So you can come and we can do a review. But, well. Okay, so that was it for the exam. Now we start kind of new block. Today's lecture is on rigid body transformations and poses. It's supposed to be practical, a practical approach, but we will need to define some little theoretical things. So today we are going to divide this class into parts. The first one, I'm going to introduce some of the concepts. Again, this shouldn't be like very theoretical. You should just get this as an introduction. So for maybe for some of you, this is a new topic. Maybe you have already studied this, right? So what we want is everyone just to get introduced to rigid body transformations in 3D. And then the second part of the class, it's going to be a seminar. So, well, Marcel will explain you about this after the second part, but basically you will see this in action, right? So, well, let's start then. Okay. Losing connection. Rigid body. Okay, so you need to remember a little what we were discussing in lecture 5 when we were talking about rigid body transformations for 2 dimensions. Remember there, what we had is we had something like this, a local frame, and then we had a global frame. This is in 2 dimensions, right? And then we were saying, look, you have a point here in this local coordinate. Actually, what you want is, calculate this point, but in global coordinates, right? So for that, what we did is something like this. So we had this, and we know that this point actually is this transformation, right? Then we wrote like this kind of notation. It goes from local frame to the global frame. And then here, what we had is this point in the local frame. Why is this useful? Because then we were saying, okay, you can transform your observations. Maybe your sensor is in this local frame, but you want to calculate poses in global frame, right? So, but we didn't really get into many details, right? For 2D, it's easy because actually all transformations, we know that they are x, y, and theta parametrization, right? So for 2D, this was easy. This transformation is just expressed with these 3 variables, and this is what you were using in problem set 2 and problem set 3, right? So on the plane, things work fine, and you don't really need to distinguish between this transformation and rigid body, this transformation and just coordinates. Now, most of you are proposing to do some projects involving 3D terms, right? So I think we discussed this last week, and some of you were doing this. Also, this is another interesting thing. So we have built already like the intuition behind all the estimation methods. The problem with 3D is that we need to work a little more on the mathematical part just to make all the algorithms that we have explained before in state estimation still valid for 3D, right? And the problem is it's gonna come from here, right? So most of this is gonna be depending on a matrix, right? And this matrix is kind of redundant. The degrees of freedom is not exactly matching the number of variables that you have here in this matrix, right? And for that, that's why we need this extra effort. So again, today's class should be very, very practical. I'm gonna explain ideas. If you have any question as we are explaining it, please ask this. And then later on the, let's say, more practical part, all these concepts should be clear, right? But if there's something that you don't see very clear, please, let's discuss this. There's also a little material in Canvas and in GitHub, if you want to take a look. There's a little more explanation of what we are going to explaining today, right? So if you want to go there and see, oh, okay, so all these things came from this, right? So there's a little more demonstration, so on well, some of the concepts, but I would say that this will be the second lecture, the second reading for you, right? So you first follow this, what we explain in this hour, and then later, if you want, you can take a look at this topic, which I think is, if you are doing like any project with 3D, or if you in the future think that you'll be working with 3D poses, I think it's very valuable. Okay, so let's now, it's working very poorly today. Okay, let's talk about 3D rotations. We start with this. Why? Because we know that a rigid body transformation is just a rotation and a translation, right? So we need to define like this element, which is, it was trivial before, it was just an angle with just the theta parameter. We were defining rotations in 2D, but for 3D it's not that simple, right? Okay, so what is this? Basically, all the matrices that are a valid rotation conform what is called the spatial orthogonal group, right? This is just notation, but now you can substitute rotations by a spatial orthogonal group, right? And, well, you'll see later why we call this like a group better than just rotations. So as I said, this is all these rotations, right? This is a 3x3 matrix. So we know about this. You have a 3D point, you rotate it, so this must be a 3x3. And then the condition for this is that we discussed this property before, right? So for orthonormal matrices, this property should hold. So this product of your transpose should be the identity. This is from linear algebra. For now, we don't really care about how or why these matrices form a group. And then there's an extra little detail, right? It's not that all orthonormal matrices are rotations. In fact, that's not true. Are only those that the determinant is 1. Okay, so this is going to be all possible rotations. Any matrix that satisfies these two conditions is going to be a rotation matrix. And then, well, we already discussed like some properties of this group, right? It was a little more informally, but if you have two rotations, I'm here writing 3, but this could be any dimension. It's 3 because this is what we are more interested now. 2, we already discussed. Now 3 is the interesting part. So this in general, well, this should also be a valid rotation, right? So if you remember, last day what we were discussing is you have a chain of transformations, right? So you still get a valid transformation. So one of the important parts and why that was possible is because rotations are just this way. So if you think about it, this makes sense. Right? Orthonormal matrices are not really changing magnitudes or anything inside, are kind of rotating. And this is why we need this condition, right? We need the determinant to be 1. Imagine that if the determinant here for some of them is not 1, right? Then, well, this product will not be in the group, right? So if you have here like, then, well, basically this property will go away and some of the things will not be like obtained so clearly. So in order for this to be valid, we need also the determinant to be 1. Okay, so let me go now for the rigid body transformations. There's still some properties from here that I'm not explaining, but the same properties are going to be true for rigid body transformations. And I think this is a little more interesting group for us to discuss. Okay, so let's come here, 3D, rigid body transformations. From now on, I'm just going to write RBT, right? And it's kind of fine. Okay, so what is this? Well, similarly as we defined before, we are going to define like this group. Now, this is what we are going to call this special Euclidean group in 3D. So you can change, this is just a change of name, right? But it's the same. So 3D rigid body transformation, right? The mathematical group that actually is the special Euclidean group. So we have this, and then the structure we have already discussed like in previous lectures, right? So here we have a rotation, here we have a translation, and then here we had these other things, right? And if you remember, this was because when you calculate things with a homogeneous coordinate, that's why we needed this extra thing. Okay, so then, as we said, the rotation should be a valid rotation, and then the translation, the translation, it's just a vector, whatever vector, right? So with this, we can create any possible rigid body transformation, right? This is kind of continuation of what we said on this lecture too. Remember, there was like some properties, some interesting properties. One of the most interesting one was you have two transformations, two rigid body transformations, right? And this should also be a valid rigid body transformation, right? So, yes, one question. Yes, this is a matrix 4×4. So, yeah, I'm advancing here a little content, but usually when you multiply this by a vector, this vector is going to be each of the coordinates, and then you need last coordinate. This is not a variable. This is just the homogeneous coordinates. I'm going to explain this in 3 minutes. Okay, but the structure is familiar, right? So we had like here some translation, we had some rotation, and then there was this thing that last time what we discussed is if you really want to multiply like a vector and transform it properly, not just rotate it, but also translate it, then what you need is this part in your matrix. And we didn't really justify, but it was just needed, right? If you want to have like a multiplication of this point really getting rotated and translated, this is what we needed. Okay, so it's not. I think we have today a little problem with the channel. Okay, it's fine. So let's give an example of this, right? What is the simplest rigid body transformation that you can imagine? It's the identity, exactly. So this also belongs to the group, right? And in fact, this is rotation is no rotation. Here, well, oops. Yeah. No. Right, so if we have this, intuitively you know that rotation, it's going to be kind of 0, right? There's no rotation, or no. And then the translation, it's also going to be, so there's not going to be a translation, right? So in terms of how we are transforming, it's not transforming anything, right? So that's also why this is called the null element in this group, right? So you can multiply any rigid body transformation and you will get the same thing, right? So this is also an important, one of the axioms of the group, right? So we need to have here, well, let's say an identity element. Okay, so for when these things are clear, are all zeros, it's really not really very challenging. We are not doing much. So imagine if we have like here, this is our local frame or global frame, then the local frame is not really going to change. Okay, so, well, before we start discussing this a little, let's see the three common uses of rigid body transformations. Okay, we have already discussed one of them. So it's just transforming points. Right? So let me just write it this way again. So we have this, and then we have this point in the local frame. Right? So this is a very useful, this is how we introduce this in lecture 5. Right? So this is lecture. But what's going to be interesting is that actually these transformations are useful for other things, right? Not just transforming points. We gave some hints last day, but now this is a little more proper. Now it's not that we can transform points, but we can transform frames, right? So how is that possible? Well, we have here whatever frame, right? And we know that this is a composition of two frames, right? So if you remember this example, these look a little like this. So we had here like, well, in this case, here this is from B to A. Then we have this from A to W, so that means that this thing here, which is the composite frame, it's just going to be the multiplication of these two elements, right? So in this case, this was like very useful. So we have AB, yeah, and then here, BW. Okay, so we discussed a little on that, how to do composition, but actually this is a little more subtle than that. It's not that you can multiply transformations and you get a transformation. It's that you can compose, right? And they have meaning. It's not that it's just a valid transformation. It's actually that this, it's going to be expressing the same thing, right? So you can do it by multiplying two different frames, or this could be just a single frame as you want, right? So then, in this case, what we are doing is just transforming frames like properly. Right, so you change them, and then we get a valid new reference frame, whatever it is. It could be as long as you want. Okay, and then there's a third one, which maybe some of you have already guessed, but with this we can express 3D poses. Right? So what is the intuition of this? Imagine that you have okay, so what can be a yeah, like, I don't know, ship. Kind of, right? It's kind of a ship, right? So you have this. Let's say that this is expressed in your local coordinates, right? And I'm just writing this way. right? Do you agree that here maybe you can add like a sensor or something, and still, when you get a point, when a point is observed from this ship, right, it's going to be aligned with whatever coordinates are here on the frame, right? So in this case, in this two-dimensional case, maybe this is x and this is y, right? So this can be also not just the coordinates to express, well, in this case, this is the center. This is not just the coordinates to express how to transform a point, but actually this also gives us information about the body by itself. So now imagine that we change all points. You take all points here in the object, and you transform them, right? So what's going to be the result? The result is going to be this, whatever object it is, into new, I don't know. It should be the same scale. Actually, transformation is not, oh, okay, you need to use your imagination. This. Okay, kind of, right? But you see the idea. What we are here doing is transforming the whole rigid body objects, right? So why is this important? Because here at the end, there's going to be like, what is this? Where is this frame looking at, right? And you can imagine this as another way of expressing this pose. So this is going to be, there's going to be a position of this new body translated, and then there's going to be a new orientation after rotation, right? So this is kind of expressing the orientation and the translation of this rigid body pose. So imagine you start having something at the local frame identity, and then when you transform in, this is actually expressing a pose. So another example, you have a pen. Here, you apply some transformation, and this pen has an orientation, right? You agree that if you change it, this is another orientation, right? So what this problem is saying is that you apply a transformation like this, and then this is still expressing a pose, right? So this object has a pose. And you can do that not before as we were doing before with x, y, theta coordinates, but in this case, we are going to be using full we are going to be using like full transformations, right? And the problem is that orientations now, we will need more variables for that. Okay, so these are the three examples. On the seminar, you will be practicing with this, seeing examples of each of them, transforming a vector, knowing these frames, what it is, exactly how all these things affect. But the idea is that if before we were just talking about transforming a point, this is not anymore what we do, right? We do more things. We can do more things. We can do frame composition, and we can also express poses, right? Yes, have a question? So I'm not really here transforming frame L, right? What I'm doing is transforming this rigid body. But this rigid body is exactly at the center of your global frame, right? Let's call it this way. And then you can think about poses, about this difference with respect to this identity and basic, and not the identity, but the most common transformation, which will be 0, 0, 0, right? Where you are. You're at 0, 0, 0, looking at 0, whatever that 0 is, right? We will define later. So this is your starting point, 0 point, right? And then the difference is that you are not really changing your frame, right? What you are having is a bunch of points or meshes or whatever it is that this object is, or actually rigid body things, infinite number of points, if you want. You transform all of them, and if there's like some axis here inside of the object, right? Because there's like an orientation in each rigid body, right? And there's also a translation. You can move it. So what I'm saying is that this, from expressing these local coordinates, all this body by itself, if you move it, if you transform it with a rotation and a translation, you can also understand this as a pose, right? So in this case, the pose is giving you the orientation, and the translation of the body. Right? It's the full body. Here we are not talking about transformation. This is going to be a consequence. So if you have this pose, it's actually expressing you two things, the pose and the transformation. You can also do the transformation with the same pose. But it's simply slightly subtle redefinition or reconsideration of things. So if you prefer to think about frames and the only thing you are doing is moving frames, it's fine. But if you have another kind of problem and you are more used to think about rigid body objects that you move, this is another equivalent view to rigid body transformation. Okay, is it clear? The three of them are valid, and they are kind of doing the same thing, right? It's the same transformation, but there's different ways of reasoning about that. Okay, so so these are the three ways of taking a look at this. I think with the example it's going to be a little more clear. But now I would like to discuss about, well, a simple fact, and it's the following, right? So T, basically, it's a 4x4 matrix, right? For 3D poses. But what is the minimum number of parameters that we need to express a 3D pose, right? For 2D, we knew that just with this parametrization, 3 parameters, that was enough, right? So you could go from one to the other, and that was enough. Now, for 3D, what is the intuition here? How many parameters would you need? I'm going to explain this more formally later, but definitely, is it 16? 6. Okay, 6. Yeah, exactly. So it's not each of the elements in the matrix, right? We know that there's going to be some parameters related to translation. In this case, we have 3 possible translations. And for orientations, well, yes, with 3 different parameters, we can express any orientation. Now the problem is that there's different ways of expressing this rotation, and this is going to be the topic for the next section, right? So again, for doing this, you have Euler angles, you have quaternions, but what we are going to explain here is Lie algebra, right? And don't be scared. This is just a gentle introduction just to explain the physical meaning of these rotations, right? And by doing this, you will see that each of these parameters makes a lot of sense. Okay, so who has used here 3D rotations? Which parametrization do you use? Double quaternion. But that will be for rigid body transformation, not just rotations. You also use quaternions. You use quaternions. You use Euler angles. Something. Tried everything. Okay, well, it's fine. It's fine. We are going to give an alternative. So it doesn't mean that it's better. It's simply, well, I think it's better, but depends on what is your objective. What we are going to be giving you here is Lie algebra, which, if you just want to express a rotation, I don't think it's better than just barely quaternions, but it's much better when you want to differentiate. And we have talked a lot about this, right? So when you want to do like estimation of a full trajectory, we had Jacobians, right? So linearization is important and optimization is important. So if you have this, I think this approach is a little more powerful. Yes, please.
Will you talk about transforming from one system to another, from quaternions, for example?
No. So your question is if we are going to be giving like the equivalencies between other parametrizations like rotations to no. There's a lot of bounds. In fact, rotations parameterized with Lie algebra are very, very similar to unit quaternions, but you need to redefine some of the things, but this is not the point, right? The point is just you to have an awesome tool that you can use or not, depends on you, but it's simply an alternative view, right? The literature here is very deep and gets scary very quickly. right? So this for today, I think we start just with this, defining a little what is this, how we can express these rotations and translations, and then later you can go as deep as you want. Actually, it goes very, very deep. Okay, so it comes from the following idea, right? What is a Lie group? It's the same definition as we gave before for group. Well, I didn't discuss all the axioms, but well, there's like some properties, and there's an extra one that should be included, which is smoothness, right? So what we are going to have here is a group that should be smooth, right? And smooth means that there's going to be little increments on your rotation, and you are going to have like well, basically, it's a time continuous signal, right? And we want this to be smooth, no discontinuities, right? So the idea is a little intuitive. You are changing your rotation. It's not like bumps or things that might happen maybe if you use, I don't know, other parametrization. Here, this change in your rotation should be smooth, right? So what is this? If rotations are just a function of time, this is the derivative with respect to time. And what this means is that this is the assumption. There's going to be a matrix, right, multiplying your current rotation, right? So this is the idea. It looks familiar, right? It's a differential equation, right? And then here, if things are smooth, well, we should have like some sort of function with respect to this change in time, right, with respect to our current state, and then something else, right? And then we want to know what is this something else. Yes, please. Oh, awesome. That's an awesome question. What to do with gimbal lock? So you don't have gimbal lock problems here. We have kind of a side effect, but it's not really going to affect us. So gradients are going to be well-defined everywhere. There's still a problem that this transformation is going to be same as with angles, right? Different values of the angle represent the same angle. So in this case, this is a surjective transformation. But gimbal lock, it's not a problem here. This is solved, right? And you don't have a constraint, same as with quaternions, right? The constraint is that you always need to be unity or, well, defined whatever. Here, you don't have constraints. Okay, let's get to this, right? So everyone agrees that things should be smooth now, right? In our rotations, imagine you are changing your head, you do this smoothly. Okay, and what do we know about this problem? Oops. We know this, right? Uy, no. That's not true. That's not true. This is true, right? This was the definition, right? We know that this is orthonormal matrices with this extra little detail on the determinant. So this should always be true, right? Our rotation matrix multiplied by transpose should be the identity, right? So what do we do with this? What we are going to do is do the derivation, right? So in this case, I'm going to derive this. You have this on the notes, by the way. Right? And we know that this should be equal to the derivative of time with the identity. Right? So far everybody agrees. I'm just putting here like some differentials just based on this condition. Okay, so if we derive this thing, I'm just here following the chain rule, we'll get something like this, right? And what is the derivative of the identity with respect to time? 0, yes, doesn't change. Okay, so we have this, and then well, there's another way for obtaining this, but I'm just using this because this is a little more simpler. I'm just going to substitute this and assume that if we are going to have smooth rotations, then this derivative is going to look something like this, right? So that means that we are going to have this. And then here, we are going to have this. Right? And those should be equal to 0. Okay, so far everybody agrees, right? You just need to, this is our initial assumption. This is what we wanted for our group to be smooth. So that's how we are writing about it. And then if we do this, this is the identity and this is the identity, right? So this always holds. Any rotation, if you translate it, here, this is one of the properties, should be identity. Yes? Okay, and here comes the condition, right? So we were talking about what is this thing? What is this matrix that is going to be multiplying? So if we want to preserve this condition on having this orthonormality on the rotations, then this transforms into this. So whatever is the derivative of this rotation, this matrix should hold this property, right? And does anybody know when this, so what kind of matrices follow this thing, this property? Exactly, exactly. Very good. So why is this important? Because this gives us like a structure of exactly how these smooth changes should look like, right? It's not everything. It's not possible to be like 3 by 3 or any number, right? So there's a structure. And then we see that skew symmetric matrices actually have some structure. So let me write it this way, right? So this W matrix is going to be skew symmetric. And in this case, I'm going to write it like this. Okay, is this a skew symmetric matrix? I mean, do the mental, you need to transpose. If you transpose it, is this equal to the minus, right? So you see here that there's this property, and this is only true if your diagonal is 0, by the way, right? If you had here an element that is non-zero, then how can you do this thing negative, right? So there's a lot of structure. Okay, there's also another way to write this, right? So we are going to have this vector, the omega vector, and then we can also write like skew symmetric matrices just with this upper thing, right? So every time that I write this omega tilde, what I mean is that this is a matrix 3 by 3 with this property. Okay, so now everybody agrees that if there's like smooth group of rotations, they should follow like this kind of rule, right? So it's going to be derivative, it's going to be multiplied by this thing plus the rotation. Yes? Okay, so now, yes? So there, as I said, there's other ways. So you're asking why is this smooth, right? Why we should be assuming that this kind of smoothness and not any other kind. There's other derivations, a couple of pages, that you end up in the same result, not doing any assumption of this kind of a structure in the matrix, right? So if you don't do this, there's still a way for you to derive this, right? But I'm just saving you a couple of pages. Right, but still, yes, you should be getting, if there's smoothness, like a structure like this, right? So derivative is going to look like this. If you are more interested on the book, here on the references in Lynch and Park book, there's very well developed this topic. The reference is at Canvas, so we have a document explaining a little of what we did today. If you want to go deeper, exactly how to obtain all these things, you can go there. Okay, so, well, we have this. Now the second thing is what can we do? So I'm going to define the exponential map. So you will see in a moment what it is, but now that we have really? Now that we have a solution, right, for the derivative, we just integrate it, and we should get a solution like this. Multiply by time, and this is the transformation at time 0. Right, so you just do you just integrate. This, right? And if you do that, you should be getting something like this, right? So this is good until the moment that you start thinking and you realize that here we have a matrix, right? So what we need to do is the exponent of a matrix, right? So maybe that's why I was giving you hints, right? Why this section is called the exponent map. So what do? Do we give up? No, of course not. So we can do two things. Well, the first one is also we are not going to be giving like a continuous time signal for this. We are going to fix t, let's say, to 1. And in this case, I'm going to define this new variable, theta. Okay, before doing that, let's discuss a little on the physical meaning of this, right? So these are, this is the variation of angles, right? Or angular velocity, if you want to think about it. Still, it's not true. It's not clear exactly what it is, but the dimensions on this should be radians divided by second, right? So we have here some sort of velocity, how much you are changing your orientation, right? So if you want to obtain an orientation, you need to integrate this, right? So that's why we're integrating with respect to time. Now, the problem is, if we want to approximate this exponential, we cannot really have here a time-varying function, but instead what we are going to do is assume that this is constant for some interval, right? And then we are going to be doing an integration. This is not really important from the point of view of representing rotations, but if you want to derive this from a physical meaning, and I think that's easier to understand all this topic, is you start with this, right? So you have your angular velocity, whatever it is, right? Now it's a skew symmetric matrix. You integrate it, and after integrating, you should be getting an orientation, right? So this is the motivation why we need this differential form. Now, we do some sort of trick here, or not magical trick, but just an assumption, and then we say, look, okay, so this can be whatever, right? This is a time continuous signal, but what we are going to do is we are just going to assume that this is constant, and we evaluated this at time 1. Right? So that's why some people, when they refer to the parametrization of rotation, they use omegas. But in fact, the dimensions for this should be angles. Right? So in this case, we are going to be using thetas. Now, theta is a 3-dimensional vector, by the way. So you see here, we have 3 parameters. So this is a vector, and then this is the skew symmetric matrix built from this vector. Okay? And then what we need to solve is this, right? So we were discussing that this is what we want, right? Solve this exponent. So what do we do? Well, a common thing to do is approximate the exponent by a known series, right? Taylor series. And with that, things should be fine. Right? So why? Because we don't really have exact solution for an exponent of a matrix, right? That's not really, there's no, I mean, you cannot, there's no closed form. Who knows what that is? But still, Taylor can hold, and actually it's going to be what we are going to be using, right? So we start just with definition of Taylor. And then a very interesting thing is going to happen. And I think, well, I'm not going to explain everything, but I really want you to get this thing about the skew symmetric matrices. Okay, so we have here the Taylor expansion. Now, is the problem better? So we have changed a function, the exponent from exponent of a matrix, which we cannot calculate, into an infinite series. It doesn't look better. No, it looks better. So it's not really like that we are winning much. Then what can we do? We can approximate, that's for sure, but then there's an even better thing that we can do. And it's basically exploring a little more the structure of the problem. And in fact, skew-symmetric matrices, if you try this later at home, you will see that they have a recursive form, right? So if you square a skew-symmetric matrix, you are going to get something like this, right? So this is, this is the outer product, right? And then here, what is removing is the well, the L2 norm, right, of this vector. So this is for the square form. And now for the cubic, what we have is if you multiply this by this, what you see is that by definition, the skew-symmetric matrix of this vector this vector multiplied by the skew-symmetric matrix, this is going to be 0, right? Because, okay, imagine. What you have is this cross product of a thing that is the same, right? So this simply goes away. This term goes away. And then what you are going to have is this, which is going to be a number, whatever it is, plus, again, a skew-symmetric matrix. So we get back to the exponent 1, if you want, right? So this is kind of a recursive thing. Squared skew-symmetric matrices have this form. Odd skew-symmetric matrices are like this, just the skew-symmetric matrices of the exponent, and even odd is to n plus 1, right? So this is the exponent here. So you see here that there's something that we can exploit, right? You have a question.
How do you get this formula for the
Well, you do the derivation. You calculate, you put here these skew-symmetric matrices. You multiply them, one to the other, and then what you are going to get is this for the square. And for the cubic, it's the same. So you start doing this. I'm just here writing what you get if you do these calculations by hand, right? So it's just the derivation, but by induction. You are not assuming anything. There's no property, nothing. You just put there all the elements in your matrix, start multiplying, and then you will see that there is this recursive form, right? And well, this is great because now we can solve this infinite series into a closed form solution. This is also called the Rodrigues Formula. And then what we see is that actually our rotation, imagine it was the exponent of this angle, right, after doing this trick of assuming a constant angular velocity for some time. It's simply this, right? Well, it's a closed formula. This is norm, by the way. Here, putting this a little bigger. This is the vector. Okay, so it makes sense, right? Our infinite series just becomes an element, the identity. We cannot really do anything with that. All the elements that were corresponding to the skew-symmetric matrices actually factorize into a sinus. And the same goes for the square of the skew-symmetric matrices, right? They factorize into this thing, this 1 minus cosinus. So we have a closed form, right? This is the takeoff. I'm not asking you to derive this thing, although yes, well, there's books doing this, but the important thing is that there's a closed form for calculating this. Yes? No. No. That's why on the lecture notes I have theta to be bold And in other places, I have just normal theta, but with my handwriting, I cannot really distinguish. But you are right, these are not vectors, these are norms, right? So you cannot really, we'll have the same problem again, right? The sinus of a vector. No, I mean, this doesn't go forever. No, this is a norm. Okay, so that's great. With this, actually, with all the parameters that are composing these skew symmetric matrices, we can compose any rotation. This actually, by the way, it's going to be called the also Lie algebra, right? Why? Because we've seen that this is the differential form of the rotation, right? And then this is composed of all the matrices that have this structure, right? So it's a skew symmetric matrices. Right? So you can also write this in terms of a base, right? So there's just 3 elements spanning this base. And let me write it just for the first one, 1, -1, right? And we can call this, right? This is the generative of 1. We can do the same for the second one. And then there's going to be a generative matrix for the third component. Right? So all I'm doing here is, okay, I'm going to put colors here. This and this, right? I started with 1, right? So we have this, which is going to be red, and this. And then I'm going to have this. Okay, what nice color, green and green. Okay, so you see here, you just remove these parameters. And then this is, so actually all this is spanning a base, right? And this is the another next connection. So it's not just that this is the Lie algebra, right? All these skew symmetric matrices for rotations, but it's that we can transform actually this group into just 3 vectors, into a vector of 3 components. Yep. This thing? Yes, you're right. So, yeah. Do I have this? Yeah, I have this correctly on the, yeah. Okay, yeah, very good. Still, that will be a skew symmetric matrix. But if you want to follow a convention, we just follow this one, right? So these 2 elements were negative, this is positive. Still, that will be a skew symmetric matrix. But you want to follow conventions, because then if someone asks you, okay, how is this skew symmetric matrices? How are you considering it? Then everyone should be doing the same. So I think here literature is common. Everyone uses the same transformation. And well, I think here comes almost the final recap of this. So if we have said that with this thing, we could go from R3 to the Lie algebra of rotation. Remember that this was doing the skew symmetric matrix, this operator, right? The exponent, actually what it's doing is going from this small, this is a small SO3, this is the Lie algebra, right? This is going to the all the group of rotations, right? So with the exponent, we can have any 3 variables that you want, right? It can be anything. Actually, we haven't said there's no limits here because, well, you see, there's going to be a problem that many different thetas are going to give the same rotation. But this rotation is unique, right? So it's basically a surjective mapping. Okay, so we have this. And then what we can do is, because we are going to be interested in more compactness, we can define this kind of, so this is 2 steps. We can define a more compact operation, which is this exponent with the capital, that it's simply going to map from R3, right? It's simply going to map to the rotation, right? So this is very convenient. We have 3 components now. We don't know exactly what they are, right? But we have this notion of them being angles, right? Exactly, they don't have to have like physical meaning because it was a little, we obtained this after considering constant fixed angular velocity for a given time. But the cool thing is that forget about the physical interpretation now. With any 3 variables, we can obtain a rotation, right? So this was a way of representing this. You have another way of representing rotations, which you have already discussed, like a sequence of Euler angles or a quaternion with a long formula and lots of other things, right? So this is another way of obtaining it. Today you will not see why this is so useful. You will see this on next lecture, but this is simply another different way of parameterizing things. Okay, so then what about the inverse, right? So for the inverse, you can still do it, right? This is going to be called the logarithm, right? So the logarithm just goes from any rotation, and then what we are going to have is a 3D vector, right? So this is awesome, because then we can go back and forth, right? Here, happens the same as with angles. Right, so for angles, this is still a valid angle, right? They are, all these multiples of k represent the same angle, so you are going to have a similar thing here, right? So that's what I was saying, it's surjective mapping. Different values of your theta are going to give you the same transformation, but this is good because still all of them are just pointing to the same element, right? So if you take the proper measurements, which is basically this norm to be smaller than this, then this is going to be a bijective mapping, right? But this is just for you to know. Still, this is good. These properties are good because what we want at the end ultimately is to represent rotations, right? All our operations now are going to happen with rotations or with translations. And if we have like here different variables, well, this might go away. Especially if you do then the logarithm, right? Because the logarithm, yes, it's gonna map them to the interval that you have defined. So it's very similar to tangent, right? So tangent and arctangent, they always map you, the arctangent always maps you back to your minus pi, right? It's not mapping you to million multiplied by pi. Okay, so I'm running a little out of time. We have explained a little this idea for rotations. What about rigid body transformations? You need to work a little more, but the same idea holds here, right? There's going to be, and in this case, this has a physical meaning, right? This matrix also is called a twist, right? So for those in physics, but we also are looking for the same kind of a smoothness, right, in this group. And if you end up doing this, as a result, you will see that we have rotations that should follow the same, rotations are going to be just as a block, so the same condition that we had before should be like true for one of these blocks. Right, so let me write it a little more formally. So we are going to have here an omega, like this. And then there's going to be another variable here on velocities, right? So let me explain it in a minute. Okay, so this part is what we did before, and now we have an extra element, right? And this makes sense because rotations, yes, they have all this structure. We are representing rotations with matrices, but it's not true for transformations, for translations, right? Translations in our matrix are just a vector, right, that we are writing here. So if we do the derivative of this, well, we are going to have, this smoothness should be preserved, and then the condition for this is going to be this. So in this, we are going to have a skew symmetric matrix in this block, and this is just going to be normal, well, not normal, but almost close to normal derivative of linear velocities. Okay, and now I'm going to skip a lot of content, but you can apply the same principle as we did before, right? So you do this, right? And this actually is going to be defining the Lie. This is going to be defining the Lie algebra of rigid body transformations, right? Now instead of having 3 parameters as we had before, we are going to have 6 parameters, right? So let me write it this way. So you are going to have omegas and then velocities, right? And this is a 6 by 1. So now this is the 6 components that you were talking about. We know that intuitively this is the degrees of freedom, but how to parameterize this changes with different, different parameterizations. With this, it's very clear, right? So we have 3 for rotations, and then we are extending this a little with velocities. This thing, by the way, it's connected. So this V is not exactly translations, but actually this takes into account rotations, right? If you see the formulas on the exponent, you will see that actually, yes, it's affecting. So this is not exactly our old translations. They have been, basically, it's because how this rigid body transformation works before we rotate and then we translate. So this is also going to be included here. Okay, so I'm almost close. What is the great thing about this? We redefine things, and we can have kind of the same mapping, right? So we are going to move from R6. Now this is this base spanning the Lie algebra. This is also called a manifold, right? This is some sort of manifold of now rigid body transformations, and with this we are going to create any rigid body transformation, right? And the same is true for the logarithm, right? So for the logarithm, you can go from any rigid body transformation, and then you are going to create a 6-dimensional vector, right? So these functions, you will have them available. You will make use of them. You can take a look on how they are implemented, but that's not really important here. What is important is that this mapping exists. It has been obtained after reasoning with this smoothness, right? These derivatives that we were talking about. And then you can make use of this. So how is this going to be useful? Because you are just going to be given some parameters in a 6-dimensional space. Here it has nice properties. And then with this, you can actually represent a rigid body transformation, right? And the same goes for the other side. So you will have a matrix 4 by 4, which is the rigid body transformation, and then you will see the parameters there, right? So the seminar is going to be about this. Okay. There's another interesting property that you might use, but I think it's better if I'm not explaining this too much. If you want, then you can digger. This property is going to be useful for some derivatives, but I think for now this is the definition of the adjoint, right? So you have a transformation like this, right? Imagine this is going to be. So this is the first transformation, right? We start here. Okay, we start here. We do this. So this is the exponent of this, whatever transformation it is. I'm just writing like this. And then we transform by t. So we know that this is going to be equal to the exponent of this adjoint, right? In this case, with respect to t, of these coordinates. And then we multiply it by t. So what is this thing saying? So let's just try to follow like the sequence of transformations. And in this case, this is what I was transforming first here. and then I'm transforming with respect to t. Now I'm going to be the opposite, so this is going to be t. You need to use your imagination. I'm not sure if this is correct. And then what we use is this thing. So you can imagine this as a way, as kind of a linear relation between the coordinates in the Lie algebra. This was with respect to the identity, and now the adjoint allows you to change them, right? Like in this way. Okay, so this is just a curiosity. It's going to be used later, but this is most useful when you want to differentiate, because then the adjoint is going to be very convenient, right? So when you have this kind of, it's kind of an equality. You can think about it like this. And very, very briefly, again, let me talk about random variables. So what about random variables? We haven't explained anything about random variables so far, right? This is, I mean, if you allow me to do the summary of this lecture, it's this thing. This is all we have discussed, right? There's going to be these two functions, mapping from this matrix of rigid body transformations to some coordinates and back, right? So you can derive it, you can just use it, that's up to you, right? But the idea is that we are using rigid body transformations. We haven't discussed about random variables. So there's still a way to calculate random variables. So if classically we use like random variables this way, right? So you have like, well, whatever constant or whatever random variable, and then we were just doing a summation. Let's say in this case, this is a normal variable, right? What's the problem now? That we cannot really do summations here on rotations. We cannot really do that, because if we do that, then that's not a valid rotation, right? You cannot do this. This is not going to be a rotation, and the same goes for. So the problem is that we need to use group operation, right? And the group operation is multiplication. So very briefly, you will see this in action. Imagine you want to do like little perturbations of some rigid body transformation, right? Something like this, right? And then what you're going to have is this, right? So and then comes the interesting part, right? So we are going to define this random variable to be, for instance, a Gaussian variable with whatever statistics you want, but this is going to be in the manifold, right? So this is a 6-dimensional variable, right? Still, with this, we are going to perturb like rotations properly, right? So this is going to be interesting. So imagine this is good for if you have particles or if you want to calculate like covariances, right? So we are basically perturbing things slightly, and this is equivalent to the summation. Remember, we don't have here any summation. You cannot really do like small perturbations inside your, so you cannot do that, right? And then do this. Does anybody know, anybody have a reason why not? Yeah, this is one good reason. But no, this is just a vector, right? So you are not applying this directly to the skew symmetric matrix. You are applying this to the 3-dimensional vector or 6-dimensional. The reason is summation is commutative, but you know that transformations are not, right? So really this is not the same as you'll be doing a slightly different thing, right? This still might give you like some perturbations, but this is not exactly what you want. What you want is always this, we are always going to be working with this idea. So the group operation is closed. You cannot really, no, not closed. It's very clear, well defined. It's the multiplication. You cannot really do other things than that, right? It's not going to be then an element of the group, the result. So that's why you can define noise in this manifold, do this slight perturbation, and still you are going to have here like good results. Yeah, because this thing is equal, right? And then basically product multiplications, the order matters. So yeah, this is no. Not allowed. Okay, lot of content, not that much. Are you ready to play around a little? See this in action? I'm telling you, this is awesome tool. Just the first day, imagine you can do on other days. But so let's see this in action, right? We have like 5 minutes, and then we'll do a little seminar. For this, I think we have a link somewhere in Canvas. So if someone has laptops, open it, and this will open a project in Colab, right? So then you will be executing things, and if you have a laptop, you can sit next to someone who has a laptop, but the idea is that everyone here should be doing things. Okay, so 5 minutes, take a look at this link, and then we will go together, try to solving all these problems. Yes? No, I just explained you how to deal. No, that will be like a lot. I prefer you to play around with the exponent and the logarithm. But yes, that's definitely a topic that will develop or can develop also deeply. So take a look at the books, because then they explain. For today, this is all we are going to say. This and the seminar. Yes, exactly. Actually, yes, we will be discussing next lecture like approaches for using this properly in our filters as well. But this is just introduction, right? So I would like to finish here, and then this notion of noise, random variables, covariance propagation there's more content there.